Okay, good morning, everybody. Welcome to virtual seminars for Precambrian geology. Today, we're excited to have Dr. Mike Kipp present for us. He's presenting on phosphorus limitations of the Precambrian biosphere. What is the evidence? What is the mechanism? And what are the implications? So I'll introduce Mike pretty soon here. Next week, we're going to have Dr. Michael Brown from University of Maryland presenting on secular change in metamorphism tracks the emergence and evolution of plate tectonics on Earth. So join for that. And last week, I had a couple announcements, and I'm going to kind of go over the same announcements today. So I'm going to share my screen and just show everybody what we need, what's coming up in the new year. I should be showing my screen. I sent this email out earlier in the week, and it's just announcing the 2022 schedule that is on the website now. And importantly, after the new year, we're going to be changing our schedule to Thursday mornings at 8 a.m. instead of Wednesday mornings at 8 a.m. Pacific time. So it doesn't overlap with any other established seminars. I also included this request for feedback Google form, and I made the classic mistake of not making it available to anybody other than people within UCR. So now that is correct. So I will post this in the chat just as soon as I finish introducing Mike, and people can go ahead and maybe after listening to Mike's talk, go ahead and do that. And also, lastly, I am looking for a little bit of help from preferably another PhD student or master's student who wants to get connected. So helping out with the seminar gives you a little bit of experience running a seminar, and also can forcefully get yourself involved with the community, and we can get you connected with people you might benefit you to network with. So with that, I'm going to go ahead and get on with business here. And so I'll introduce Dr. Michael Kipp for us. So Mike received his bachelor's degree in biological sciences at the University of Notre Dame, and his PhD was at University of Washington, working with Roger Buick, where he studied nutrient cycling in deep time and its relevance to exoplanetary research as well. He's particularly recognized for his work on the global phosphorus cycle. After his PhD, Mike spent a year as a visiting scholar at Australian National University, and he's now a postdoctoral researcher at Caltech, continuing to expand on his research using stable isotope geochemistry and biogeochemical modeling to study the redox history of the ocean atmosphere system and its impact on the cycling of macronutrients. So with this, Mike, I'm going to let you go ahead and get started. So go ahead and share your screen and take the stage.
Cool. Thank you, Alex. Just a moment. All right. Is that coming through?
Yeah, we see you and we can hear you.
Perfect. All right. So yeah, thank you for that intro, and thanks everyone for tuning in today, whatever time zone you're in. And yeah, thanks for Alex and Andre just for hosting this in general. It's been a lot of fun to tune in to these talks all year. In particular, to get people's chance to give feedback and get discussion and debate going on different topics in Precambrian geology. So I hope to do that today and get some maybe lively discussion or even debate going at the end. So please, encourage any and all input. So the topic I'll be discussing today is one that I think has, over the last several years, gained some some popularity and thus some controversy in the Precambrian community, which is the role of phosphorus in limiting the productivity of the biosphere, the largely marine Precambrian biosphere. And this talk is going to have something of the layout of a review talk. So what I want to do first is just kind of quickly go through, in a first order sense, the lines of evidence people talk about when they invoke phosphorus limitation in the Precambrian. And then I want the main bulk of the talk to be diving a bit more closely into the mechanisms that have been proposed to sustain this nutrient scarcity and try to use some geochemical data and simple models to judiciate between these different potential mechanisms. And then finally get to, at the end, the different implications that, say, a given mechanism of phosphorus limitation would have for the rise of oxygen or the evolution, say, of complex life. All right, so let's dive right in. So why even talk about phosphorus in the first place? What is the role of phosphorus in the biosphere, or specifically in what I'm talking about when I say biological productivity? So the reaction I'm referring to when I talk about biological productivity can be sort of generalized, as you see here, where what life is doing in biomass building reactions or anabolic metabolism is taking inorganic carbon, reacting it with a reductant, an electron donor, and creating organic carbon or biomass with some byproduct. And so a bit more specifically, what this looks like, we have our inorganic carbon, which is in the form of CO2 or perhaps dissolved inorganic carbon, carbonate or bicarbonate ions in the ocean. And our biomass here we could approximate in shorthand as CH2O, reduced carbon. And then there's a variety of reductants or electron donors that we know life can use with corresponding byproducts. And if we're thinking about, say, Earth's early anaerobic biosphere, for instance, we know some potential electron donors that are utilized, say, by bacteria, archaea, include hydrogen sulfide, reduced iron. And not only can some of these be used, say, in chemosynthetic metabolism, so that is where we have a chemical gradient powering the forward progress of biomass building reactions, but we know that some of these substrates can be used in anoxygenic photosynthetic reactions. So we know there are iron oxidizing or sulfur oxidizing phototropes. They harness light energy to do this. And we know that this has been prevalent through Earth's history, going nearly as far back as the geologic record shows us. One of the nicer lines of evidence for this is just the prevalence of stromatolites, these upward, clearly photosynthetic microbial structures that you can find. In this case, an example in the Death Valley area 1.3 billion years ago, but reaching back 3.5 billion years ago or more. So we can sort of do a back of the envelope calculation, and that's what papers like the ones I'm citing here have done, to approximate the productivity of such a biosphere using these electron donors. And those estimates largely derive from estimates of the flux of, say, hydrogen sulfide or reduced iron to Earth's surface, under the assumption that this is the limiting reactant in this forward reaction. But as we all know pretty well in this seminar series, something really dramatic happened at some point in Earth's history, which was the evolution of oxygenic photosynthesis. So a metabolism harnessing these two photosystems, getting this larger potential that allows splitting of the water molecule with O2 as the byproduct. And we care a lot about the implications of this O2 byproduct, but right now, what I turn our attention to is the fact that this was an enormous leap with your electron donor then becoming ubiquitous in the form of water. So you're not going to be water limited living in the ocean. And another way to put this is that this advent of oxygenic photosynthesis then presumably ushered in the era of nutrient limited productivity. That is, we would not be limited by electron donors. We have an abundant source, or at least a large source of inorganic carbon in the atmosphere ocean system. So it's other constituents in biomass that would contribute to this reaction. So that's strictly speaking, I guess, what we're talking about today when we talk about nutrient limitation. And as for what part of Earth's history that involves then, so just to put us on geologic time here. Stephanie talked a bit about this last week if you were in that talk, so I'm not going to rehash all of the lines of argument for or against early oxygenic photosynthesis. Just suffice it to say, we agree pretty well this must have arisen by the timing of the Great Oxidation event about 2.4 billion years ago. And there are a variety of lines of evidence suggesting that some hundreds of millions of years before that, this metabolism already likely existed. So if that is the case, we then need to talk about nutrient limitation of that biosphere. Okay, so we still don't have phosphorus in this equation. So how do we get there? What I'm going to do is take this oxygenic photosynthesis reaction and simplify our equation here. And then we'll have to expand it to include terms that get us to all the way to phosphorus. And to do that, we have to include the next two most abundant constituents of biomass. So nitrogen and then phosphorus. And what we see here, if you look now at this expanded sort of recipe for marine biomass that's drawing on this stoichiometry called the Redfield ratio, we see that carbon, hydrogen, oxygen, and even nitrogen are all readily available either as seawater or in the atmosphere in the form of carbon dioxide, or N2, which we know can be fixed into biomass by certain prokaryotes, including cyanobacteria that can execute oxygenic photosynthesis. So it's not until we reach phosphorus that there is a constituent of biomass whose supply dominantly comes from weathering of the continents, which we know is an orders of magnitude slower process dealing on geologic timescales. So this is really the basic line of reasoning that points to phosphorus as the geological timescale limiting nutrient. That is to say, on million-year timescales or longer, it's the supply of phosphorus and its availability to marine life that controls the forward progress of this reaction. Okay, so if we take that, we care about phosphorus, but how does it actually cycle then through the ocean atmosphere system? So I'm going to show maybe an egregiously oversimplified cartoon of the marine phosphorus cycle. So my apologies if your favorite flux is not in there, but we could talk about it if you'd like. But in sort of broad brush strokes, what's going on here is that we have, like I was saying, delivery of phosphorus to the ocean dominantly through draining of the continents or rivers. A sizable chunk of that is actually thought to be non-reactive, not bioavailable, and actually just is removed in sediments rather quickly. But that which is reactive or bioavailable is quickly taken up by photosynthesizers in the surface ocean. So this is its role as a limiting nutrient. You see evidence of this in the form of phosphorus depletion in surface waters. So this is being nearly quantitatively assimilated, and that biomass then we know would eventually sink through the water column, these organisms die, and it would be making its way to sediments. But in fact, there is a vigorous recycling, or we call it remineralization flux, that is actually returning most of that organic carbon and with it its nutrients, so phosphorus, back to seawater. And so this is actually very effectively recycling phosphorus within the ocean. And you see this occurring in deep waters. In one way, as deep waters age, actually they accumulate more and more of this phosphorus as more of that remineralization has occurred. Eventually they are upwelled to the surface ocean. Again, this can be supplied back to photosynthesizers. So this recycling gives phosphorus a moderately long residence time, something on the order of 10, 20,000 years is our current thinking. So that's the recycling within the system, but eventually phosphorus gets buried, and the largest flux that's transporting that phosphorus towards marine sediments is this export production, organic matter sinking. And so this is organic bound phosphorus making its way to sediments, but in fact, once it reaches sediments, it can meet a few different fates, or it can undergo what we call sink switching. So it can be buried with the organic matter, it can stay put, it can continue to be remineralized, like is happening in the water column, so returning back to the ocean. And then it can also be trapped in other host phases, so including iron phosphorus phases, or even through precipitation of authigenic apatite minerals. And there are other removal fluxes. So for instance, adsorption directly onto iron oxides that can be important in the modern ocean, say near hydrothermal efflux. So these are sort of the major fluxes in the phosphorus cycle, and to just give a sense of scale, orders of magnitude. In the modern ocean, we think there's about an input flux of on the order of 2 teragrams of phosphorus per year, bioavailable phosphorus, which may sound like a lot, teragrams, it's 10 to the 12, but that's about 3 orders of magnitude smaller than the internal recycling flux. So per year, in the modern ocean at least, the amount of total phosphorus that's used by life in this biomass producing reaction is actually due to the recycling rather than the new input of phosphorus. All right, so that's how we think the modern phosphorus cycle vaguely works. And I sort of led the talk with this idea that some people have invoked a scarcity of phosphorus in the Precambrian ocean. So what's that all about? So to sort of just prime us for thinking about this, which is probably something abundantly clear to a room of Precambrian geologists, but what we're talking about when we think about scarcity of phosphorus in the Precambrian ocean is the amount of this phosphate, let's say, the size of that reservoir, the amount that can be taken up by organisms. And we, of course, don't have any direct record of that. So we have no samples of ancient seawater reaching anywhere near Precambrian age. And instead, what we have is the geologic record. So ancient marine sedimentary rocks, say, deposited in different environments, capturing some different combination of these phases. And what we're trying to do is use those facies, those preserved remains of what was going on in the ancient ocean to figure out not just what was happening at this proximal site of deposition, but actually what was the size of that reservoir and net uptake. And as we'll come to see, it's actually not so easy to do. So like I was saying from the beginning, the way I want to start the sort of evidence side of the talk is just to quickly walk through the major lines of evidence and types of lithologies that people have looked at to invoke phosphorus scarcity in the Precambrian ocean. I'll move pretty quickly through these and then we'll dive back in a bit more detail to each one. So we'll walk through iron formations, shales, and phosphorites. And I'll start with iron formations, largely for chronological reasons. So in fact, the paper that could be said to have kicked off this whole notion of phosphorus scarcity in the Precambrian ocean, at least with an empirical record, is this paper in 2002 in Nature by Bierman and Canfield. What they did here is measured not just the total amount of phosphorus, but the phosphorus to iron ratio in some late Archean and Paleoproterozoic iron formations. And their motivation for doing so is perhaps twofold. So on the one hand, it was known at this point for about 3 decades that iron oxides near hydrothermal plumes in the modern ocean would scavenge phosphorus efficiently. And so on the one hand, this is just a conceivable analysis to undertake. There's enough phosphorus to be measured. But actually a few years just before this paper, there's this study showing that in those hydrothermal particles, the ratio of phosphorus to iron actually very nicely tracks the ambient dissolved phosphate concentration. So like I had mentioned before, this varies, say, in deep waters of the ocean, among other reasons, is a function of water mass age, as more and more remineralization occurs. And so what you could conceivably do then is go to some ancient iron-rich sediment, where perhaps phosphorus was being scavenged onto iron. You measure this phosphorus to iron ratio and you use the slope to calculate the ambient dissolved phosphate. And so that's precisely what they did in this paper. And so now you're seeing their reconstructed deep water phosphorus concentration. And what you'll note is that this is about an order of magnitude smaller on average than the modern average value, which is something in the order of 2 micromolar. You can see that as the average of these data points here. So this implies an order of magnitude smaller phosphorus reservoir, all else being equal, at this point in the late Archean and Proterozoic. And some started to refer to this as the Archean phosphate crisis. So perhaps there was an extreme scarcity of this nutrient and the biosphere would have clearly been limited in its productivity at that point. So it gets a little more complicated. Actually, a few years later, then Kurt Konhauser and others came through and pointed out that you need to account for differences in seawater chemistry between the modern and Archean ocean, in particular, the abundance of silica that we would expect in oceans prior to the evolution of silica precipitating organisms. And so you might have actually been approaching silica saturation, maybe 2 millimolar, which would mean that effectively your silica could outcompete phosphorus for those binding sites with iron. And so you could actually have, in these experiments they did, very high ambient dissolved phosphate, yet very low molar phosphorus to iron ratio. So this slope down here. Whereas in the modern ocean, those hydrothermal particles we just saw, there's this steeper slope. So this would really complicate the interpretation. Basically, it would mean you can't really say much with that proxy record. And some years later, Carey and Jones and others revisited this with even more of a treatment of competing ion absorption. So here you're seeing calcium and magnesium that they're inferring to have changed through time. They again did these calculations assuming different silica concentrations in seawater. Indeed, you see at the highest silica, you reconstruct higher phosphorus. So here we're looking at, again, 1 to 2 micromolar, something like today, whereas it's lower if you infer lower silica. So it's maybe not as clear as it once seemed, but the sort of first order interpretation of this data set to date largely remains that it's showing us lower than modern phosphorus in the Archean and Proterozoic. And perhaps there are details that are difficult to resolve without knowing seawater composition in the Archean more precisely, but this is sort of the first order takeaway that is discussed. Okay, so we can move then to a different lithology, which I'm calling shales here for simplicity, but really it's a little broader than that. So I'm referring to this study by Chris Reinhardt and others a few years ago, where they made this enormous compilation and also some new measurements of just the abundance, weight percent phosphorus in marginal marine siliciclastic sedimentary rocks. So they're looking at just these lithologies that are thought to capture basically deposition, broadly speaking, on continental margins. And in a first order, what they see here, aided by the different colors, is that on average, there's about a factor of 4 lower phosphorus content in Precambrian shales than in their Phanerozoic facies equivalent. And without yet diving too much into the mechanisms they invoke for this, if we return to this schematic, they're pretty much inferring something to the effect of there being a smaller reservoir, so less phosphorus available, less uptake, and thus less export, so that the entire burial flux was muted. And like I said, in a moment, we'll get into why there may have been that smaller reservoir, smaller inventory. Okay, so at least the interpretation offered of this data at the time, so in that paper, was that it seems easy to explain this record if there was a lower phosphorus concentration and muted burial flux. All right, and then the last line of evidence I'll introduce are phosphorites, which are a kind of exotic facies. So these are exceptionally phosphorus-rich marine sediments, so they can reach several weight percent, if not tens of weight percent phosphate. And actually, if you look back at the same Reinhardt paper, they included a panel here with just the number occurrence of phosphorites in different age bins. This is coming from earlier work, actually some decades ago, compiling phosphorites around the world. And you see that there's some clear temporal structure here, and it's not quite the exact same as this phosphorus abundance in siliciclastic sediments. So you see no Archean phosphorites. They show up in the Paleoproterozoic, perhaps less so in the mid-Proterozoic, and then again in the terminal Proterozoic into the Phanerozoic. These may look like small numbers, but it's actually quite striking. So again, you go from having no Archean phosphorites to, in the Paleoproterozoic, finding dozens of examples present on all continents. So something clearly changed in phosphorus burial in marine settings. And just to stress the point, so here's actually the cover photo that we were looking at. This is from the Zanega Formation in Russia. So this is 2 billion years old, one of the older phosphorites. This is actually a picture of a deposit being mined. This is an exceptionally organic rich rock called shungite that's associated with the phosphorus-rich horizons. And this is all just to say these are enormous deposits. So this is a non-negligible change in phosphorus burial. And again, at first order, this record then seems to point to muted burial of phosphorus in these types of settings, at least in the Archean and perhaps mid-Proterozoic, and clearly something changed in the Paleoproterozoic and Neo-Proterozoic, seemingly increasing phosphorus burial. So a first order interpretation, again, is that you're increasing the amount of phosphorus in seawater. All right, so that was kind of a quick run through lines of evidence that people invoke for phosphorus scarcity in Precambrian seawater. But if we think a little more closely about it, actually what they're all pointing to is muted phosphorus burial. And that's what we actually have a record of. So any further inference about the size of the phosphate reservoir, the mechanisms controlling its cycling, rely on models that we put forward and then our ability to test those predictions. But actually what we're directly seeing is muted phosphorus burial in these settings. And in the literature now at this point, there are a few different schools of thought about how that could have been maintained through the Precambrian. And I've sort of distilled these into three schools of thought here that I'll walk through, and then we'll try to dive a bit deeper into the predictions of each and see if we can test them. So the first school of thought I'll call iron scavenging, and this goes back to that original paper of Pierre Canfield, but it's actually been reworked, rehashed by many others at this point. And the basic idea at the original conception of it is that by analogy to these, say, modern hydrothermal plumes with iron oxides that we know adsorb phosphorus quite readily, you can imagine in an Archean ocean where we have this voluminous iron deposition, you would have had much higher iron content in your seawater. So you should have much more vigorous scavenging of phosphorus from those waters, and you could effectively scavenge it all away. You'd trap it in the deep ocean, choking off the supply to the photosynthetic biosphere. So at the original conception of this idea, it was supposed that this was an iron oxide adsorption mechanism. So again, this is by analogy to the modern iron oxide scavenging today. Also prevalent thinking at the time that iron oxides played a primary role in genesis of iron formations. But now we know on the one hand that we think reduced or mixed valence iron minerals may have played a role in iron formation deposition. And we've also seen accordingly that reduced and mixed valence iron minerals can scavenge phosphorus in different settings. So at this point, this mechanism is not specific to iron mineralogy. All right, there's a second school of thought that says basically you don't need to invoke iron scavenging. So in fact, the characteristic we know of reducing waters, so not just low oxygen, but actually low oxidant, so including sulfate scarcity and so on, is that organic matter is very efficiently buried. And with it, then what that basically means, the corollary of that statement is that phosphorus is not remineralized back to the water column, either in the water column or in sediments. So in other words, this mechanism invokes a flux of phosphorus to the ocean that is efficiently taken up and then efficiently buried. You don't sustain much recycling, so you have a low steady state phosphorus concentration. So Ava Stukin and I put this idea out there a few years ago. It's also been really nicely delineated in a few papers by Tom Loxo and Dan Schrag that I'll talk about a bit later in the talk. And then there's a third school of thought that differs from the first two because it actually invokes a larger than modern phosphorus reservoir today. Like I said, what we're actually looking at are mechanisms for muted phosphorus burial, not necessarily phosphorus scarcity. And what this model draws upon is the observation that in modern anoxic settings or in recent anoxic sediments, say from the Phanerozoic, we see evidence that phosphorus is efficiently recycled. Actually, so this is sort of the antithesis of this model. There's enhanced phosphorus recycling. You struggle to bury it despite burying organic carbon. And so what this model invokes is actually in the Precambrian, you see, say in the shale record, these low phosphorus concentrations because you struggle to bury the phosphorus there, but you're efficiently recycling it in the ocean. And so this actually implies that there's high productivity in such an ocean and a long residence time, I guess, of phosphorus. So this was first put forth in a Precambrian context in this paper by Lenton and others in 2014 and has been expanded upon recently. We'll come back to those papers. So these are the three mechanisms I want to try to sort of pit against each other, test the predictions of. And I'm going to do so pairwise to keep it organized. And so I'll first set aside this one that's a bit different, and I will try to compare the two mechanisms that invoke low phosphorus concentrations in seawater. And I'll do so by asking what I think is a pretty simple first order question, which is how did most phosphorus reach marine sediments in, say, the Archean early Proterozoic? Because I think these two models have pretty clear end-member predictions. So in the iron scavenging model, we'd say most phosphorus should be entering sediments with iron. If that's not the case, then it's sort of not really limiting the biosphere productivity because it's making its way to biomass. In this other model, then we would expect most phosphorus to be entering marine sediments with organic matter. So it's not being liberated to have the chance to be scavenged by iron. All right, so I'm going to pit these two against each other, and I'm going to look in the place where I think we would be most likely to see evidence of iron scavenging, which are iron formations. So we know there was voluminous iron deposition occurring. The Archean Ocean, for instance, we have a more nuanced understanding of this today than we did some decades ago. So we know there are probably differences in primary mineralogy as a function of depositional environment. We also know in all these cases, though, those iron minerals can scavenge phosphorus from the water column. So I think it's not a grand leap of logic to say that if this process was occurring, we should see some evidence of it in iron formations. And there are two ways I'm going to try to look for this. They're both pretty simple, but I think a powerful way to get just a first order assessment of the role of iron versus organic matter in bringing phosphorus to sediments. So in both cases, what I'll do is look a bit more closely at actually iron formations that were included in this original study of Bierman Canfield. The first is the Dales Gorge iron formation. So this is right near the Archean Proterozoic boundary in Western Australia. And I'm actually going to be drawing on work that was done by Kurt Konhauser and others in a paper in GSA Bulletin a few years ago. So what they did was considered not just the amount of phosphorus or the amount of iron in the Dales Gorge iron formation, but they also considered the abundance of other trace elements. And they asked the question, could you best explain the abundance, not only of phosphorus, but also relative to these trace elements, with a source being adsorption to iron minerals, so here ferrihydrate, or with the source being export production, that is sinking of organic matter, bringing these constituents. So this is the exact test that I was saying we'd like to conduct. And the way they did it is that they took the measured concentrations of phosphorus in these trace elements in the Dales Gorge iron formation, and they cast it here in the y-axis in terms of a metal flux per year. So in order to do that, they need to make some estimation of the depositional rate. And so in doing so, they can then turn their concentration data into metal flux per year, which is what you see here. So it's worth noting that the relative pattern here is not dependent on the depositional rate estimate. So that's just the relative concentrations. The absolute position on the y-axis is a function of the depositional rate estimate. And then they asked the question, can we better recreate this with this biological source, biomass, or with this iron mineral adsorption source? And they did this experimentally. So they cultured photosynthetic bacteria, so cyanobacteria and iron oxidizers, photoferrotrophs. And in this case, they did abiotic iron adsorption experiments. And here's their data. So what you see on the left panel is that in all cases, so here's photoferrotrophic biomass and cyanobacterial in green. In all of these, you see that the relative pattern of phosphorus and trace elements is nicely matched by the biomass source. If the depositional rate estimates are accurate, then it seems that the photoferrotrophs would do a better job of getting you the necessary annual flux to match what's observed. And contrast that then with the ferrihydrate adsorption, which in theory can get you the amount of phosphorus that you observe, let's say if you have the right amount of iron, but it would struggle then to explain the amount of observed molybdenum or cadmium. You can flip that around and say, if this was the source getting you the molybdenum and cadmium, you would have an excess of phosphorus that's beyond what you observe. So this means that it's sort of difficult to invoke a vigorous adsorption source for these trace elements in phosphorus when you so readily can explain it with the biomass that we think was being deposited at that time. So this is one line of evidence, in other words, to say that it looks like phosphorus was mostly entering these iron-rich sediments with organic matter, actually not adsorbed onto iron. Okay, and there's one more way I would like to look at this, which is going to involve diving into a different iron formation. So we'll jump over to South Africa. So this is the Crewman iron formation. And I'm also going to look at the Greequatown iron formation. So these are Paleoproterozoic of South Africa. And we're going to just look very simply at the phosphorus abundance, so weight percent phosphorus, and the total iron concentration. And I'm going to make a very simple claim, which is that if this scavenging is occurring, like in the modern ocean, you see on these hydrothermal plumes, there's a very clean slope, phosphorus over iron, very constant slope, if you account for, say, a single ambient phosphorus concentration. we should see then in these data, if the iron is the dominant source of phosphorus, something of a clean positive correlation. Maybe it gets muddied during diagenesis and so on, but there should be some level of positive correlation if that's the dominant source of phosphorus. And in fact, we see no clean correlation. So it seems hard to say that adding more iron is adding more phosphorus in these settings. And the flip side, then we could do the same test and say, well, you should then be able to see evidence or lack thereof for a correlation with organic matter. This is a bit more complicated though, because actually, so there's this well-known paradox about iron formations that they contain very, very little organic carbon today when you look at them. Yet we think that export of biomass must have been quite vigorous to these settings. We think there is an important biological role in the depositional environments that led to these iron formations. And it seems one way that we often explain that paradox is that there is abundant diagenetic oxidation of organic matter, for instance, through ferric iron reduction. As we know, there would be abundant ferric iron. So one way that you could estimate the original organic carbon content, I'm drawing on work here in this other paper by Kurt Konhauser and others, including work from Clark Johnson's group, is to say you can reconstruct the original TOC by measuring the existing amount of organic carbon, and then also adding this term, which is an estimate of the amount that was lost during early diagenesis. And this is done by measuring the inorganic carbons. This is carbonate, largely in the form of siderite in these settings, and then using the isotopic composition of that siderite to estimate the fraction of it that was derived from oxidation of biomass. So if you make some estimate of the original delta 13C of biomass, so it's usually isotopically very light compared to carbonate, let's say 30 per mil or so lighter. Then when you measure these carbonates coming out very isotopically light, pushed in the direction of the organic matter, that's telling you there is a contribution of that organic matter. So if these have the same value, that would mean 100% of the carbonate came from the organic material. Okay, so if you do this sort of simple calculation, look at the organic carbon data, you actually see, at least in the case of the Crewman, that there is somewhat of a correlation between the phosphorus and the original organic carbon concentration. And even in Creekertown, when it's not a clean correlation, what I would point out is that in all of these cases, if you look at the carbon to phosphorus ratio, the carbon to phosphorus ratio, we think, using this primary organic carbon value, is much higher than we would expect for primary biomass at the time, which was maybe, you could say, the modern Redfield ratio around 106, or maybe elevated due to nutrient scarcity. In any case, we are higher than that, meaning given the amount of organic matter we think was deposited, you can easily explain getting all of the phosphorus there from that biomass. So just to put this another way, it seems, again, just through this simple exercise, that it's much easier to explain the phosphorus being sourced to these sediments with organic matter. That does not mean it's staying bound to the organic matter now, but that's the source flux that we should be thinking about. So I think these are pretty simple ways of getting at the problem, but I think they do test these hypotheses nicely. But one follow-up that's going on, and I think will really improve our knowledge of this, is being carried out by Jana Meixnerova up at University of Washington, where she's looking here at the Mount Sylvia formation. So this is below, here's the Dales Gorge member that we were talking about before. So this is Western Australia, latest Archean. And in the Mount Sylvia formation, there are alternating horizons of shale and iron formation, meaning we can do this sort of calculation in these different lithologies. And what I think that will help us test is whether, you could say, oh, is this reconstructed original TOC actually accurate? Well, that's not really necessary in shales, for instance, because we don't have this abundant authigenic carbonate phase a lot of the time. So stay tuned for that. I think that will really help expand upon this sort of initial way of thinking about this problem. So just to sort of quickly sum up what we looked at there, I think given these first order ways of looking at sources of phosphorus to marine sediments in the Archean, it looks like this organic source was dominating even in these iron-rich settings. And so that would point to some amount of role of this limited phosphorus recycling in phosphorus limitation of the time, if it were occurring. But given that, then what I want to next do is compare this limited recycling model to this seemingly antithetical model of enhanced phosphorus recycling. So to do this, I really want to dive into what are the chemical conditions or the specific chemical reactions that would actually drive this enhanced recycling versus limited recycling. In other words, how can we have the same data interpreted in pretty much polar opposite ways? So I think we can resolve this discrepancy. And the way I'll do that is by starting with the tracing back the school of thought that is the enhanced recycling of phosphorus in anoxic sediments. So if you trace those papers back, you'd originally come to this work by Ellery Engel and others in 1993. What you're seeing here is data from the New Albany shales. This is Devonian to Carboniferous in southern Illinois, Indiana. They also compile data from other Paleozoic and Mesozoic shales in this paper. And in these units, there are laminated black shale horizons, so that we think were deposited under anoxic bottom waters, and those are these filled triangle symbols. And then there are bioturbated oxic horizons, which are these open symbols. And something that's quite striking at first glance is, okay, we see much higher organic carbon in these black shales, so that is no surprise. But you also see less phosphorus in those black shales. So in other words, the carbon to phosphorus ratio is much higher. And what the authors inferred at that time then is that there was enhanced recycling of that phosphorus back to the water column, or in other words, you're struggling to bury it in these anoxic black shales for some reason. Now, this is based on ancient marine sediments, but this paper was quickly followed up with some modern ocean work, so using benthic flux estimates to constrain the burial efficiency of phosphorus, again, using the same symbols, so in anoxic versus oxic settings. And you see an order of a factor of maybe 2 or 3 increase in this burial efficiency of phosphorus in oxic settings. So taking all of this together, these authors interpreted this as evidence of modern and Phanerozoic anoxic sediments having less efficient phosphorus burial than oxic, or more recycling back to the water column. And to just illustrate then what this looks like to really drive it home. So here's sort of our schematic again of how we think the modern, mostly oxic ocean cycles phosphorus. In these anoxic settings, what they're basically saying is you inhibit the formation of these other host phases, or perhaps dissolve them if they exist. And you also promote continued remineralization of this phosphorus that then will escape the sediments into the overlying seawater. So this is pretty interesting to think about in terms of a mechanism that can control feedbacks in the Earth system. Because at first blush, you might say, okay, anoxia gives you enhanced recycling of phosphorus back to the water column. That will sustain more phosphorus uptake, so greater productivity, which sinks, creates more oxygen demand, more anoxia. So this is a positive feedback for ocean anoxia on short timescales in the ocean. But there's also an interesting long-term feedback, which goes in the opposite direction, which is that as you continue then through that intensified anoxia to recycle phosphorus, you are burying the organic carbon. You see that here, the form of high organic carbon contents. You will eventually generate atmospheric oxygen through that. That greater atmospheric oxygen would enhance the oxygenation status of the ocean. So this is on long time scales, perhaps a negative feedback on atmospheric and marine oxygen levels. So all of that sort of thinking was put forth in some papers following on this initial work. So there's this now seminal science paper by Van Kaplan and Engel putting forth the idea about this negative feedback on longer time scales through the Phanerozoic. And there's some papers taking that positive feedback, thinking and applying it to ocean anoxic events, thinking of how enhanced recycling of phosphorus might sustain ocean anoxia during OAEs. And it was only a bit later then that these ideas started to be applied to the Precambrian, and people started to say, okay, we see this evidence of very different anoxic phosphorus cycling than oxic, and we know the Precambrian ocean was anoxic at depth through billions of years. How did that impact the Precambrian phosphorus cycle. And so you see these ideas making their way into these models. And I now want to pause and say, we need to dive yet another step deeper into what specific chemical reactions are facilitating or actually driving this enhanced recycling in modern anoxic settings. And do they actually apply to the Precambrian, or is something different about seawater chemistry that would mean this model doesn't apply? So what I mean by that, I'll illustrate here. Here's this environmental cartoon again of enhanced phosphorus recycling. And so in modern anoxic settings, what we think is going on is twofold. So on the one hand, you have this enhanced or extensive and progressive degradation of biomass, so proliferation of phosphorus remineralization. And this occurs because even when we deplete, say, local bottom waters of oxygen, or pore waters, sediment pore waters of oxygen today, there's an abundance of other electron acceptors, most importantly sulfate in seawater, which we're never going to fully deplete today. We have 28 millimolar sulfate with millions of years residence time. It's an enormous reservoir. And so you can sustain the remineralization of biomass even in strongly anoxic waters today. And a corollary effect there is that the byproducts of some of those reactions, so let's say of sulfate reduction producing sulfide, will actually compete with phosphorus, say for binding environments with iron, so you'll form sulfides, pyrite. And so that iron then is not going to trap phosphorus, it's locked up as sulfide. And so what these all in turn mean is that you continually release phosphorus from organic matter today and have nowhere else to put it. You don't put it in iron phases. You also can inhibit authigenic apatite formation with abundant sulfide. So this is the mechanism by which we think this enhanced recycling plays out in the modern ocean. But if we consider, say, the Archean, things were quite a bit different. So here's a compilation we made a few years ago of electron acceptor availability in seawater through time. And we know that not only would oxygen have had a much, much lower equilibrium concentration in surface waters as we go back in Earth's history, but we think sulfate levels were orders of magnitude lower than they are today, reaching micromolar levels maybe in the Archean as inferred from sulfur isotope systematics. So one thing you can do with this, which is what Ava and I did in this paper a few years ago, is take the stoichiometry of organic matter oxidation reactions through each of these different electron acceptors and just calculate at steady state the maximum amount of phosphate that you could maintain in just a 2-box model, so in your deep ocean box, if you used all of the available oxidants. And in that really simple calculation, what you see is that today we have an abundance of oxidizing power well in excess of the actual deep water phosphate concentration, which is again about 2 micromolar. But if you look at the Archean, we make different assumptions about the carbon to phosphorus ratio of primary biomass. But even in the most conservative case, here at this 106 ratio, you would struggle to reach even half of the modern phosphate concentration. So noting this is a log scale. So it may have been quite a bit lower. So this is largely driven by the scarcity of sulfate at this point in Earth's history. And so what my takeaway from this then is that the scarcity of sulfate in the Archean, maybe mid-Proterozoic, where it's much less well constrained, would imply that we'd be in the limited recycling regime as opposed to enhanced recycling. In other words, this sort of toggle between anoxia giving you limited recycling or anoxia giving you enhanced recycling is very sulfate dependent. And another way to sort of up the complexity of this calculation that I'm currently working on is taking models like with the architecture of these that I was discussing before, and saying, if we go into this remineralization flux, let's explicitly account for other electron acceptors, namely sulfate, which have not been included to date. So they've only relied on oxygen and then have assumed that in the absence of oxygen, you can just remineralize biomass infinitely, sort of like today. And just some really preliminary data. This is very much work in progress, but some preliminary model results from taking this sort of a simple model, only considering a single box, and then in accounting for sulfate scarcity. What I'm showing here is the effect on the carbon to phosphorus ratio in sediments, and on the deep water phosphorus concentration as a function of surface ocean oxygen levels. So here, the blue band represents modern values, so we're at the 200-300 micromolar range. In the Archean, maybe we're at micromolar levels in oxygen oases, like Stephanie talked about last week. And if you assume a modern sulfate reservoir, 28 millimolar, then in both of these cases, as you reduce oxygen concentrations, you actually don't impact phosphorus, carbon to phosphorus ratios or phosphorus steady state bottom water concentrations, unless you account for some of those mechanisms of enhanced recycling, which I didn't explicitly do in this black line, but would push you, say, up in this direction or this direction. So that's the enhanced recycling direction that you see today. But if you run the same calculations with a small seawater sulfate reservoir, so micromolar, tens of micromolar concentrations, you're pushed in the opposite direction. So your carbon to phosphorus ratio in sediments will eventually just resemble that of primary biomass, because you're not remineralizing that biomass. And likewise, your maximum steady state deep water phosphate concentration will then be maybe an order of magnitude lower. So this is very much work in progress, but what I think it's showing is the important role of sulfate in toggling between enhanced versus limited recycling of phosphorus in anoxic settings. Okay, so to come back to these models, again, like I was just saying, I think there's this important role of sulfate. And if we're talking about the Archean, then I think that puts us perhaps in this limited recycling regime, for which I think we should then consider the implications. So that's what I'll finally do here, is to say, if this mechanism of phosphorus limitation occurred at any point in Earth's history, then what does that mean about, say, the rise of oxygen or the rise of complex ecosystems? There are two implications I want to point out. So the first is this one that I had been stressing just before, which is that sulfate was a key regulator, I think, of Precambrian phosphorus burial. And to illustrate this, I'll put up again this estimate of electron acceptor availability in seawater through time. This low, say, micromolar, tens of micromolar sulfate in the Archean was actually, we think, largely sustained through volcanic SO2 emanations that were then photolyzed in the atmosphere, giving you some sulfate flux. So on the one hand, it's just interesting to think that maybe in this early part of Earth history, we had, to the extent that sulfate was driving remineralization, it was largely volcanically supplied. And so there's some maybe astrobiological implication there, the rate of volcanism impacting your phosphorus recycling. But we also know at some point then, oxidative weathering eventually turned on. So you have this new supply of sulfate to the biosphere. And at that point, then we would imagine in this model, you enhance the recycling of phosphorus, you get that positive feedback maybe going. And so this oxidative weathering really, and growth of the sulfate reservoirs is maybe playing an important role in phosphorus burial at these junctures in Earth history where we think there was a redox change. And to look for evidence of that, what I got thinking then and putting this together is that maybe you can find evidence of this change in these very early hints of oxidative weathering in the late Archean. And so what I'm going to show here is data from the most famous of these, which is the whiff of oxygen in the Mount McRae Shale 2.5 billion years ago, Western Australia. And this was identified through this enrichment of molybdenum, which is redox sensitive, thought to indicate pulse of oxidative weathering. And at the peak of that pulse, then this gray interval that you're seeing here, in later work using iron speciation, Chris Reinhardt and others inferred that this was actually euxinic deposition, whereas deposition before and after was anoxic, but ferruginous, not hydrogen sulfide containing. And so that already points in the direction of an extra sulfate source, perhaps at the peak of this, maybe due to oxidative weathering. And then what we see in the carbon to phosphorus ratios, actually quite strikingly, is an increase to high C to P, like we see in modern anoxic settings or recent anoxic settings, whereas you do not see that before and after. So this is actually really, I was actually kind of shocked that it comes out that cleanly. It's maybe showing that with this enhanced sulfate availability, you're recycling more phosphorus, inhibiting the formation of other phases, just like today. And what also supports this inference of an extra source of sulfate are sulfur isotope patterns. So if you look in the lower shale, you see that actually the mass-independent Cap33 sulfur isotopes have this clean slope when plotted against delta 34. So we think this is an atmospheric signature in the late Archean. Whereas at the peak of this event, you actually see, despite delta 34 variability, very muted Cap33S variability, which would imply dilution of that with an extra source of sulfate, which would not carry the mass-independent signature. So that would be oxidatively weathered sulfate. So my takeaway from all this is that an increase in sulfate availability promoted enhanced recycling of phosphorus at the peak of this whiff of oxygen. And so in other words, we might be observing one of the first times in the geologic record when we transited from limited recycling of phosphorus to enhanced recycling, all the while with anoxia in deep waters, but hydrogen sulfide present here, whereas it was not before and after. And so this, I think, may have played an important role, say, in feedbacks leading up to the great oxidation event. You'd stimulate greater recycling and productivity, oxygen production, and so on here. And I just want to point out that the same sort of thinking has been applied recently to the Neoproterozoic. This is from one of Tom Loxo's papers, showing that they infer an increase in marine phosphorus that's associated with rising sulfate concentrations and recycling by sulfate-producing bacteria. Okay, and then a second implication that I just want to quickly point out that I think is cool has to do with the distribution of biological activity in the Precambrian ocean. And here I'm also going to draw on one of Tom Loxo's papers, because he did this nice thought experiment where he said, consider a two-box ocean, one that's near the continents, one that's deep. In the near shore box, you have a source of phosphorus from weathering, also from remineralization and upwelling. Offshore, you only have the remineralization and upwelling flux, no weathering. And so, like we've been saying, if you cut off that recycling flux due to this low sulfate, low oxygen, then in nearshore boxes, you'd get some amount of phosphorus from weathering, but you'd get basically none in deep water boxes. So this says that in the simplest sense, biological activity should be concentrated in nearshore environments. And this actually really nicely lines up then with observations, say, from the microfossil records. This is going back to work of Emmanuel Javot, 2001. This is from the mid-Proterozoic. We're looking at eukaryotic microfossil species richness and abundance, which peaks in nearshore environments, diminishes offshore. And this is also borne out in nitrogen isotope gradients. So we see evidence of nitrogen availability, maybe active aerobic nitrogen cycling in nearshore environments, diminished activity offshore. So another interesting implication is that this limited recycling model would imply a nearshore biosphere where you supply phosphorus, it's taken up, and then it's quickly sedimented out. And maybe this plays an important role in the delayed rise of eukaryotes. Okay, almost at the end here. So I just want to point out that in terms of ongoing work, I'm really interested in this question of how we can better distinguish between these mechanisms of phosphorus limitation. And to do so, I'm diving into this phosphorite record specifically. So this means doing some field work, getting drill core samples, and trying to use multi-proxy studies to really understand each case in its own right. So whether there's a control of redox, sulfate, weathering, and so on the deposition of these phosphorites, and whether that changed, say, from the Paleoproterozoic to the Neoproterozoic and Paleozoic. So some of that work was recently published, and some's actually being carried out at UC Riverside by Ginny Winters, doing a senior thesis there, and also Jana Meixnerova, again, at UW, who's looking at this more recent example of the Phosphoria formation, seeing if it actually resembles these older phosphorites or not. All right, so finally, just some distilled conclusions from all that I've put forth today. So I think we see this evidence, going back to the early part of the talk, that phosphorus was mostly reaching Precambrian sediments with organic matter, not iron. And because there is a high burial efficiency of that organic matter, you would have had limited recycling of phosphorus back to the water column. So this could have kept phosphorus levels low in the Archean, maybe in the mid-Proterozoic. But the key regulator here is the marine sulfate concentration. And so I think what was causing us to transit between this limited recycling regime and one in which anoxia gives you enhanced recycling is perhaps growth of the marine sulfate reservoir. And so I'll leave you with this model schematically of how I'm sort of envisioning this, where perhaps there's this time in Earth's history in the Archean, we have limited phosphorus recycling, low availability. something changes in the Paleoproterozoic, we have enhanced phosphorate deposition, perhaps limited recycling again in the mid-Proterozoic, and before enhanced recycling comes back more recently. And I'm making the case that at a first order, I think this is closely related to growth of the marine sulfate reservoir. So I think that's a suitably speculative note to end on. And so I will just close by thanking all of these folks who have made this work possible over the years, as well as all of my funders. And I'm really happy to take any questions.
Thanks, Mike. That was great. We're going to go ahead and we're going to transition to our question session, which is usually done either by virtually raising your hand, typing a question. I can ask it for you if you'd like to type the question. Looks like, Paul, you had something, but it got answered by the end. So if you want to ask, go ahead and throw your hand up. But otherwise, it looks like Jun is ready to ask a question.
Sure. Thanks, Mike. That's a wonderful talk. And also, I like your paper very much. Totally agree that phosphorus limitation in the recycling aspect is the key. My question is related to the follow-up of or the natural consequences of your mechanism, because in order for that to work, I think also Louis' modeling work also shows similar trend, is that your oxygenic phosphorus has to be in the dominant phases after the sink switching happening. So I wonder, because you're mentioning you have done some field work. So I wonder, do you expect to find some proxy or any line of evidence to show that calcium phosphate or vivanites was in the more dominant phases during your, say, limited recycling phase?
Yeah, great question. Thanks for that. So maybe I don't fully grasp it correctly, but my initial thought to what you're saying is that what I'm really invoking with this limited recycling is about the transport to sediments. And so that's why in the approaches I showed towards the beginning, I was trying to use just this bulk rock stoichiometry to get at whether most of the phosphorus arrived with iron versus with organic matter. But that has no requirement really about where it currently resides. I guess on the one hand, you would say if there's limited oxidation, then it would have to stay even in the sediments in the organic phase and not enter these other phases. But small changes in that I don't think negate the net effect of the limited recycling model. So I think it's hard to really test that with that, like basically the phosphorus speciation work, which I think is really interesting and tells us a lot. And that's, some of this new work going on coming out of Leeds, where they're looking at different operationally defined phosphorus host phases. But yeah, the question of how it got from whatever brought it to the sediment to whatever phases it's currently in doesn't, I think, necessarily answer the question of how it got there, and thus what was the dominant mode of limitation is one. Right, does that answer your question?
Right, I totally agree. The reason I ask is I'm a little bit skeptical about using the C2P ratio in the sediment to infer the, whether there's a limitation or recycling, because you can have sink switching, say reduction of iron oxide hydroxide, reduce and may liberate phosphorus. But if that phosphorus was being captured by calcium immediately, then you have a sink. So that's why I totally, and I also like your idea of the self-limitations. That would prevent it from become a sink again for the phosphorus. But that's actually leads me to another follow-up on that. When you evoke sulfate, is I'm sure you're probably aware of the supplement figure of Chris 2017's paper, where he shows that on the silicic sedimentary rock for the both anoxic and oxic sediments, there is no differences statistically speaking for the phosphorus content, or which means that there's no differences on the phosphorus sequestration in both the anoxic and oxic setting of the Phanerozoic. and I wonder what's your thoughts on that one.
Yeah, so I guess to that last question, and also part of what you were getting at before, some of this it really gets back to this question of what you're looking at in your tests of anoxic versus oxic, more degradation versus less, and this carbon to phosphorus ratio. So going to that that early Engel et al. 93 paper, what they were actually looking at is the higher carbon to phosphorus organic ratio, so organic carbon to organic phosphorus. Like you were saying, there's the potential then of phosphorus that was liberated from organic matter but trapped in other phases. And so maybe that's not the best measure index to look at to gauge this anoxic enhanced recycling effect. And so there's a paper, Anderson et al. 2001, 2000, where they basically said they took the stance in the modern and recent anoxia setting of saying you should look at the organic carbon to total, or they said total minus detrital phosphorus. Basically, that's actually what's going to tell you whether there's enhanced recycling or whether the sink switching is just trapping all the phosphorus. So to your first question, that's the way I was actually, that's the data I was showing is carbon to the total phosphorus, not just to the organic phosphorus, because I think that better does capture whether other sinks retained it or not. But that same issue applies to the question you just asked, which is what is the actual role of anoxia or progressive remineralization, all of this on phosphorus burial, and whether it can sink switch or not. And it's actually kind of complicated because a lot of these studies are looking at the carbon to phosphorus ratio. It's helpful because then you don't need to get absolute rates for either one that well. You can just know relative to organic matter burial, is your phosphorus burial more or less efficient? And then you can plug that into your model of what the effect of this or that depositional environment is. But some of these settings that are doing a control of higher sedimentation rate or greater anoxia and all of this also have varying inputs of terrigenous organic matter, which we know today has an order of magnitude higher carbon to phosphorus ratio. So in plants, it's something like 800, 1,000 on average, as opposed to 100. And these, typical ways of doing the organic carbon to phosphorus or the carbon to total phosphorus don't adequately separate that component out. And so that actually really muddies, even in modern settings, the correlation between phosphorus burial and anoxia or sedimentation rate or all of this stuff. So I would just, that's one cautionary note, I think, that gets layered on top of the interpretation of, like in that supplemental figure you're talking about, that I think you kind of need to target, like with, I don't know, some modern studies, carefully separating those sorts of contributors. Hard to do in deep time.
Right, Mike, I totally agree. We should be very careful in making interpretation of the data, which I totally agree with everything said, except one minor things, which is when you're talking about organic phosphorus to total phosphorus ratio in the sediments. I'm not sure how that was being done, because even in the modern marine sediment or in the soil phosphorus, there is a difficulty of separating or even in the definition of what's organic phosphorus is, because insofar as I can tell, in the marine sediments, we cannot tell the differences between organic phosphorus and microbial phosphorus, which but the later categories, by my mind, is just a subcategory of organic phosphorus. But due to the lab technique we're adopting, we cannot differentiate the two. So I just wonder how you think about, say, organic phosphorus to total phosphorus in the sedimentary setting, how we can tell the differences.
Yeah, I mean, for those reasons, I think it's really hard. If anything, like the big overprinting issue that I was just mentioning about terrigenous input plant material is conveniently not a concern in the Precambrian. So in a sense, it's actually easier to say you're looking at some change in the carbon to total phosphorus, and it's more likely related to some environmental phenomenon than just influx of different material. But to calibrate that with modern studies, then all of a sudden you have that issue of separating these phases. And I don't know what people's best guess on sorting that out is right now, but this is sort of why I'm taking this really simple stoichiometric approach, is that it feels like an oversimplified way, but it also, I think, avoids some of the issues of trying to look at the actual host phases or all these other details that are maybe less clear than just the first order. Was it coming with organic matter, coming with iron? But I don't know. Maybe that's the limit of how far we can get. Maybe not. But yeah, does that help?
Yeah, thanks, Mike. That's great.
Yeah, thanks.
Diraj, did you want to ask a question?
Yeah, I was asking the Paleoproterozoic stromatolites in India and Neoproterozoic stromatolites in China are main repositories of the phosphorite. What role these stromatolites played in concentration of phosphorus in their columns?
Yeah, that's a great question, and it is kind of enigmatic that we don't have a good modern analog of. So you see modern, people say proto-phosphorite formation occurring in upwelling regimes today, and that's clearly a different depositional setting, in an upwelling like these organic rich shales that are also phosphorus rich, than what you see in some of these Paleoproterozoic, Neoproterozoic settings that appear to be these shallow water settings. They're often stromatolitic, and you see this carbonate-rich, phosphate-rich depositional setting that, that's part of what I'm hoping to sort out is to what extent is that just like a nearshore analog of what we think is this other like deeper upwelling thing, or to what extent is that actually some different depositional effect? But yeah, it could be related to any number of things at that point. Weathering inputs, some people think that your calcium supply has a lot to do with it, or your alkalinity, it could be a pH thing as opposed to also just redox and sulfate. I think when you get to those restricted basins, it's harder, like a lot more things are on the table because it need not represent the global ocean.
All these stromatolites indicate they are shallow water, and the phosphorus being concentrated in a shallow water, in contrast to general idea that the phosphorus concentration is higher in the deeper sea.
Mm-hmm. Yeah, which I agree is strange, and I think it's a very interesting question that I'm trying to chase down in a few ways. Is to what extent does that tell us something about what's happening in the global ocean or in deeper water equivalents, or to what extent is that just a shallow water phenomenon that we have differential preservation of through Earth history? Those are two sort of end member interpretations. They are not fully mutually exclusive, but I think they're kind of both on the table for a lot of these.
Just one more question. One, will it sort of affect the organic carbon isotope, the values of organic isotopes because of the presence in the stromatolites?
You mean of the phosphorus or just in that depositional setting?
I mean to say that the isotopic composition of these phosphorites, will it be affected because of the presence of the stromatolites or not? Will the stromatolite play any role in this?
I mean, I guess the way I typically think of that at this point is less of them playing a direct mechanistic role as opposed to being like a marker of a type of depositional setting in which we think there are carbon isotope effects. So that depositional setting being shallow water, perhaps restricted basin, and by analogy to some more recent environments or even deep time compilations as a function of facies at this point, people are starting to point to these enrichments of carbon isotopes recorded in carbonate, but also perhaps shifting the whole reservoir, including organic, in these restricted basins or settings in which you might find stromatolites. So I think they might co-occur, but mechanistically, it may not be just because there's a stromatolite there that's happening. Is the way at least I'm thinking of it, but it's not fully sorted out.
Thank you.
All right, I think Paul wants to address the question he asked from before, and then we have Greg in the chat. So go ahead and start us off, Paul.
Yeah, my original question was, if phosphorus was buried more efficiently in the sediment, then it should be eroded more efficiently when that sediment is deformed, which of course is an ongoing process. And I thought maybe you answered it by saying that the erosion flux would only affect the coastal waters. But the problem is that that's where the productivity is in the modern ocean also, because that's where the upwellings are. The modern ocean, of course, the erosion flux is trivial compared to the upwellings. But if you're going to run the argument that it's the flux is going into the sediment, you have to worry about the erosion flux, not least because if you don't, then you're going to have oxygen right away.
No, that's a great point, which is not
Yeah.
one I was trying to address with the nearshore offshore argument. That was sort of just under an assumption of some uniform input flux, but something I would be very interested in doing, and kind of it naturally would follow on from the like really preliminary calculations I showed, is to actually put this into a model that's going to track the evolution of these reservoirs through time, so you can actually account for the uplift, the subsequent erosion, weathering of those nearshore sediments that you, just like you're talking about. So it actually balances in the end. Like, where does that put us? And is that sustainable on long time scales? Is that consistent with what we see? To me, the bigger concern up front was also like back when we first started thinking about this years ago, is just the simple oxygen flux from burying that much organic material. Even the trivial influx of phosphorus, it can add up to a sizable, it depends what your assumptions are about the carbon input flux to the surface reservoir, but it can be a sizable amount of oxygen production, potentially problematic for keeping low atmospheric oxygen. But there's at this point, I feel like it's been demonstrated for both the Archean and Proterozoic, you can balance that reasonably. But I think we're at this like second order finer detail level now of having to account for effects like the one you just mentioned. Yeah.
Okay, so another question from Greg Italic in the chat. He says, this pattern of availability could be entirely a matter of supply from soils. Is anyone looking at phosphorus depletion in paleosols through time?
Very good question. So another thing that's been looming in my head this whole time is how we are disregarding, or at least in the way I presented it today, which broadly I think represents the literature on this. We're often disregarding the changes in the input and mostly thinking about the output. This is how a lot of the trace metal redox work has gone too, because in, say, modern anoxic events, that's what you're focusing on, is changing that output flux, assume some constant input. But the input change could be sizable and important here. So to your question about looking at paleosols, I think there's some work from Nathan Sheldon's group that I saw recently where they're looking at this phosphorus and paleosols through time. I don't remember the full takeaway, but so there's some attempt to get at it from that side. And something I also plan to include in this just continued modeling is accounting for differences in input. So we could certainly imagine, you could kind of imagine going in either direction of more intense chemical weathering, higher CO2, so on, but also less continental exposure. So these are all on the table. I think it's worth just testing to what extent those change the conclusions.
Okay, I saw a thumbs up from Greg, so I think he was happy with your response. Looks like Shuhai is now ready to ask a question, so go ahead, Shuhai. Shuhai, you might be talking and you're muted still.
Sorry. Yeah. So great talk. I sorry I don't have a working camera. But my question is, maybe I missed this when you talk about the width of oxygen in Archean. And since that you're saying that during the WIFs, phosphorus cycling is enhanced, that would mean that the buried efficiency is less, but the diagram actually shows that you have more phosphorus buried in the shales during the WIFs, or is
yeah, so to clarify, so that was actually, that plot was the carbon to phosphorus ratio.
Oh, okay, I'm sorry.
So
yeah.
when that goes up,
Okay.
it was actually less. Yeah.
All right, yeah, sorry, I misread that. Yeah, thanks.
Yeah, no problem. Yeah.
Mike, I have a few comments and questions.
Yeah.
So first, I think whatever way you go inferring anything from ion formations is very tricky. Like if you follow your model, like you bring phosphorus with organic carbon, and when you remineralize it, and whatever will be scavenged by iron, whatever iron oxides would depend on scavenging ability of iron oxides, which by that time would not be fresh anymore. So it's like whatever trend you had from organic carbon removal will be changed by scavenging on iron oxides, and it will be, we don't even know which way it will be changed, because by that time it's not anymore fresh iron oxide hydroxides. So I think, to me, saying anything from my information is very questionable. On the top of it, we don't even know in what form, what were primary minerals that formed iron formation. And second question, so if I understand correctly, you're implying that phosphorus was largely removed to organic carbon, and yet we don't see a very high phosphorus content in these shales. So, like, the only way you can reconcile it by inferring that was more burial of organic carbon in Archean and larger aerial extent of black shales. But when it goes against low primary productivity in Archean and in Precambrian, so it's kind of hard to reconcile it. So maybe you can comment on it.
Yeah, so two thoughts. So to your first point, I agree that dealing with the iron formation data is very tricky, and I'm hesitant to really start tinkering with it. But in that case, at least, with the way that that calculation was set up, estimating original organic carbon, you can set it up so that you can be conservative in not missing any possible original organic matter, which you could even add another step beyond what I did. So there's whatever you measure, it's pretty negligible. There's whatever you account for using authigenic siderite and making some assumptions about carbon isotopes. And then you can do a further step. It's also from that review paper and stuff that Clark Johnson was doing, where it says you can make the extreme assumption that all of the iron was ferric, and then any produced iron has its redox equivalent in the form of primary organic matter. So you call that the magnetite correction, where you just account for the stoichiometry of the amount of iron 2 that would get you to iron 3. That may, like you're saying, we don't know the primary mineralogy in any of these cases. That's a grand leap, but you could do it to get the most conservative estimate of original organic carbon. And then you can't do that for phosphorus, because like you're saying, you can measure what's there, and then you know that's a lower limit, and it may have been more. It may have been some respire that couldn't sync switch, like you were saying, to the iron oxides. So that is tricky, because then it was possible that you brought more phosphorus originally. I don't know a great way to get around that. I think that's just like a caveat of dealing with iron formations. And part of why I also want to look at the shales, specifically in that Mount Sylvia case that Jan is looking at now, to see, like, do we get grossly different senses of what was bringing the phosphorus there when we look at the shales versus the iron formations? Because maybe that calculation is really missing a lot of phosphorus. So I agree, that's a concern. The second question about invoking a lot of organic matter burial, basically. This one, I don't have, well, so I've been thinking about it a lot. Maybe it's not going to be a satisfying answer. But what we tried to do in a paper, let's see, it was earlier this year still, with David Catling and Josh Chrysanthemum-Totten, we tried to account for, using this like enhanced burial efficiency model, account for how much carbon, organic carbon, can you actually bury, and accounting for the amount of phosphorus we think was available, and just using all those published first order estimates that I showed. And then under different assumptions of carbon inputs through time, can you actually match the input to the output, even if you had low productivity? So phosphorus limited productivity. And you actually very easily can, because the burial efficiency can be so astronomically higher compared to today, orders of magnitude higher. So today it's 0.2, 0.4%, 0.5 of originally fixed carbon, so of primary production. And you can imagine a scenario where you crank that up to 20%, so 2 orders of magnitude. And then you can balance the inputs, but you're actually executing a large amount of organic carbon burial. It's not at odds with low productivity, because you're burying enough to balance the inputs, but and so you're burying just volumetrically a lot, maybe even more than today. But it's just a larger fraction of that which was originally made. So that, from just a carbon cycle mass balance perspective, I think what you showed was plausible. But then you're creating another problem, which is that you're producing oxygen by doing that. And so that's like a constraint from the top down, where you can say, okay, can we reconcile this with inferred oxygen levels? And in the Proterozoic, one of Tom Loxo's papers got explicitly at that question, and you basically said, here's where you would be on burial efficiency space, and you keep it redox balanced, and that works pretty nicely. That's his 2018 paper. And then what we got at in our paper earlier this year was for the Archean case, and we found that actually it's hard to explain a low oxygen Archean with that much organic burial unless you had a stronger reductant flux than today, which some people invoke for variety of reasons, mantle redox change, so on and so forth. But so you create some problems there, but there's, I think, ways around them. It's less problematic for the Proterozoic, I think.
Yeah, we can talk more, but I think some of organic carbon you recycle in Archean from older rocks. So in that sense, what you see, and that this old organic carbon will not remove phosphorus. And other constraint on burial of organic carbon just from carbon isotopes. So you would have carbon isotope excursion if you bury too much. But I'm wondering if you have a upwelling zone and you bring in phosphorus and iron and you increase productivity, I bet sort of scavenging on iron oxide would be much faster way compared to biological productivity to remove phosphorus, because scavenging would be on a scale of days, whereas biological productivity would be probably much longer. It could be an interesting way to model it.
Yeah, I think a lot of it does have to do with that. What is the actual burial efficiency rate? And then how much does that mean you're recycling? And I think to get at that accurately, we need to, what I've shown is like these simple, 2-box models of like how much at max, upper limit can you sustain? But I think you need to get into some more like spatially resolved modeling to say, okay, here's where the remineralization would occur, here's where the scavenging would occur, and can you actually, like, getting to the kinetics of it, say that this is plausible or not? So yeah, it's not to say, even throughout the way I maybe oversimplified the presentation of it, they're not mutually exclusive. I think there's room for scavenging via onto iron and room for burial of a lot of organic bound phosphorus. At first order, it just seems striking that there's no clear sign that the phosphorus is arriving with iron. And that's, I showed, again, it was the messy iron formation data, but we've looked at those sorts of patterns in shales already, and there's nothing obvious staring you in the face that it's iron. So it's not to say it's not, but yeah, we don't see anything like the signatures you see in these hydrothermal sediments today, where phosphorus to iron is a nice correlation.
Okay, thanks.
Okay, well, if there aren't any other questions, I think we got quite a bit of discussion in today. So that's great.
Thanks everyone for sticking around.
Anyway, so great job today, Mike.
Thanks.
It seems people really enjoyed it.
I appreciate
see
the
you all.
questions.
See you all next week.
Bye.